Alright, so section 5.3 is on solving trig equations, and there's really only a couple steps at the end that make it different than just solving an algebraic equation. So at least for the first few problems, I've got it set up where we're going to talk about it in like an algebra context, and then we'll look at what we would do different if it was a trig equation instead. So over here on the left of number 1, if I ask you to solve this, hopefully you would add the 1 over first and then divide by 2. And in an algebra problem, that's it, you're done. You've got what x equals. Now that same logic is going to be the first couple steps over here to the right. So you can add the 1 and you can divide by 2. Difference is you're not finished here because we don't know what x equals, we know what cosine x equals. But you need to see how those first couple steps are the same. Any of these questions we get to, even if I don't write out to the side like it's algebra equivalency, you can always do that for yourself. You can see what steps you would do this is the same steps you would do for that. All right, and then to go a little bit further, we're just asking ourselves, where's cosine 1/2? So we will need to review unit circle here, and it's at pi over 3. And then also 5 pi over 3. Okay, so if the directions say give the solutions between 0 and 2 pi, that's what you should circle as your answer. Now, sometimes, I think on our quizzes normally, not that we've finalized this year's quiz or anything, but about half the questions have these directions and half the questions have these directions that say solve. And solve, that implies you need to figure out everything, not just the stuff between 0 and 2 pi. So yeah, pi over 3 might be 1, and 5 pi over 3 might be 1. But what if I started at pi over 3 and I went all the way around, where I went all the way around 20 times? Those are different angles, and they would still be solutions. So what we would need there is you need to add 2 pi in. So we're adding integer multiples of 2 pi. And what this is really doing is it's making sure we get all the coterminal answers as well. So based on the directions, your answer could be this, or it could be that. You don't usually need to write them both ways, but we're going to write them both ways in the notes so that you get used to both ways. Okay, so not a big deal. Really the only thing that gets a little bit harder, I guess there's a couple questions that just look a little different that you need explained to you once. But really the main thing that gets harder is solving the equation get harder. It's not always just undoing subtracted times. So next example, this one looks like a quadratic, and hopefully you remember solving quadratics enough to know that you want everything on one side set equal to 0. So in a trig equation, it's not an x, it's a cosine x, but we still want that same first step. We want everything on one side set equal to 0. Then over here, I guess you could pull out quadratic formula, because quadratic formula can always solve quadratics. But I know that you don't want to. You would always hope that this guy would factor. So no coincidence that we asked you to review factoring recently, so that makes that a little bit smoother for you. But the way this factors is going to be the same way that this factors. It's just that instead of an x, it's a cosine x. You can still FOIL that together to see that it gives you the same thing. So again, 2x, 2 cosine x, minus 1, minus 1, x cosine x, plus 1, plus 1. Exact same structure. Okay, then in algebra, if this times this is supposed to equal 0, if I could make this go to 0, then the whole thing goes to 0, or if I could make this go to 0, the whole thing goes to 0. So you set each one of these factors equal to 0 and solve. And in algebra, you would be finished. We need to do the same thing over here. Set this equal to 0 and solve, and set this equal to 0 and solve. Now the difference is, because again, up to this point, I'm not really doing anything different. It just looks harder because cosine x looks more intimidating than just a regular x, but the logic is exactly the same. Okay, so now I want to think about, well, where on the unit circle is cosine 1/2, and where's cosine -1? Just like quadratics can have multiple answers, trig equations can have answers come from multiple pieces here. And if the directions say list them out between 0 and 2 pi, looks like one of them would be pi over 3, one of them would be pi, and one would be 5 pi over 3. So that could be your answer to that question, if that's the directions. If the directions say solve instead, it just means you need to say not just pi over 3, but anything coterminal to it, also pi and anything coterminal to it, and also 5 pi over 3 and everything coterminal to it. Alright, now one thing that we can practice, you don't have to do this, but if you check your answers in the back of the book, it's never going to write it like this. Well, sometimes it will. It kind of depends on the question. This particular one, and I need you to write this in your notes because you may change your mind even if you think you don't want to do it right now. You can actually condense these three statements into a single statement this time. You could say, my first one's at pi over 3. And instead of going all the way around to just get its coterminal angles, what if I just went from here to here? I would be adding 2 pi thirds. And then what if I added 2 pi thirds again? Well, that would land here that I want. And then what if I added 2 pi thirds again? Then I start getting the coterminal angles. So you can get away just saying start here and add 2 pi thirds and do integer multiples of those. And this one statement is saying the same thing of all three of those. And again, I don't have a preference. On a quiz, I would be happy to count this right. I'd be happy to count all three of those right. But just for your own sake, it's good practice to do this. Back of the book is going to write them like this. If you decide to do college trig course someday, you know, their solutions are going to look like this, and you need to know where that comes from. So you might practice it, and then if you don't feel comfortable on the quiz, you don't have to do it. All right, the next one is one that you should probably put a star by, because this is probably the most common algebra mistake that I see in this section. And I get why people do what they do here, but you got to break this habit. So you guys are so trained to say, well, as long as you do it to one side of the equation, it's okay as long as you do it to the other side of the equation. And that's mostly true. And the temptation here is, well, why don't we just divide both sides by x? So you get x equals 1. That keeps your sides balanced, and that's okay. But unfortunately, we lost an answer when we did that. There's another number squared that's equal to itself. Anybody think what that is? No. Because if you plug the negative in and you squared it, that would be positive, and this would still be negative. How about 0? 0 squared is the same thing as 0, right? So dividing both sides by a variable like that, it might get you part of the right answer, but you're also losing part of the answer. So you need to make yourself a note. Don't do that. I know it's tempting, but by far the most common mistake that we get here. Okay, so instead, what you can do is you could subtract the x over. I mean, it's a quadratic, so I just said this a minute ago. Solving a quadratic, you want it all on one side set equal to 0. So subtract that over, factor out an x. where this equals 0 would be a solution, and where this equals 0 would be a solution. So if you approach this one by dividing both sides by cosine, then yeah, you might get some of the right answer, but you're not going to get the whole thing. You need to subtract the cosine over, just like I subtracted the x over. You should factor out the GCF, just like I factored out this GCF. I should set this factor equal to 0 and maybe get an answer from that, and set this factor equal to 0 and solve and maybe get an answer from that. So I've really worked the same question twice so far. It's just in the trig part, we didn't have to say, well, where is cosine 0? At pi over 2 and 3 pi over 2. And where's cosine 1? At 0. So, I mean, that could be your answer if that was the directions. The directions were instead solve, then you just have to write it out a little bit more. This answer plus everything coterminal, this answer plus everything coterminal, and this answer plus everything coterminal. Now, if you wanted to condense your answers here, you could do it a little bit, but these aren't all equally spaced out. Like, these are spaced out by pi over 2, but then those are spaced out by pi, and then pi over 2. So you couldn't condense this into one statement, but you could say that one of them is 0 plus 2 pi n. That would get me this guy. And then you could condense these two into one. You could say one of them's at pi, and then if I added pi, I get this one. If I added pi, I get that one. So just add multiples of pi instead of 2 pi. These two statements say the same thing as those three statements. All right, so different algebra trick that I would be concerned about, that we certainly ask you to do, would be like number 4. So I think everybody would be pretty comfortable the first couple steps. Add 1, divide by 2. So over here, add 1, divide by 2. Then in algebra, to get rid of a square, we take the square root. So if we want to get rid of the square, we're going to take the square root. Now there's two things I'm concerned about for you on this question. One is, when you take the square root of both sides, it's really plus or minus. So if you forget that piece, you lost half your answers there. If that's not something you think that you might have done, you need to put a star and make yourself a note. Square root both sides, plus or minus. And 2, you have to know how to take the square root of a fraction. So taking the square root of a fraction is the same as taking the square root of the numerator over the square root of the denominator. The square root of 1 is 1. And then you could rationalize it. So again, it's what I'm about to do on the trig part here. It's like, yeah, the last couple steps you wouldn't have done in an Algebra 2 course, but what's really difficult, or where you can make the most mistakes, is here at the beginning. So we really are focusing on this algebra piece. Take the square root of both sides, so I've already got my plus or minus. Square root of a fraction is like taking the square root of the numerator over the square root of the denominator. And I really want it rationalized over here so that I recognize. Square sign is positive square root of 2 over 2 and negative square root of 2 over 2. 4 places. Okay, and if you know your unit circle well, you ready for this answer? Looks like pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Those are the 4 places between 0 and 2 pi that would make that equation work. if the direction said solve, which means give every answer, not just the ones between 0 and 2 pi, you could make 4 statements saying this one plus the stuff coterminal to it, and here's the second answer plus the stuff coterminal to it, the third answer plus the stuff coterminal to it, and the last answer plus the stuff coterminal to it. And that's fine. I wouldn't count that wrong. Mathematically it's correct, but you could condense all 4 of those into a single statement here. It's a lot more efficient and not nearly as annoying to just say, well, the first one's at pi over 4, and I can see these are all equally spaced out. If I added pi over 2, I land here. If I added another pi over 2, I land there. Add pi over 2 again, good. Add pi over 2 again, good. I start getting the coterminal angles. So if I added multiples of pi over 2, integer multiples of pi over 2, that's also fine. So a lot of times it really doesn't make a difference, but you can see this is a lot easier to write out than all 4 of those, but they do say the same thing. Okay, so again, you might highlight as we move along through here, but what I'd really be concerned about, what I see in past years from students making mistakes, forgetting the plus or minus when you take the square root of both sides, and making sure you know how to deal with the square root of a fraction. Square root of the numerator over the square root of the denominator. It's just not, I'm sure you've been taught that before. You don't get to practice it often though, so it's easy to forget. Okay, so moving on. Now let's say, what if we have some different trig functions mixed together? So like we have some sine stuff and some cosine stuff. I mean, I guess you can try to factor this if you wanted to, but it's not going to work. There's no way that you can factor this with these different trig types mixed in like that. So instead, you're going to have to go back and say, well, wait, I could replace this with some cosine stuff, because sine squared theta plus cosine squared theta equals 1. That was our most common Pythagorean identity. And if I solve this for sine squared, I can see it's the same thing as 1 minus cosine squared. So instead of sine squared, I'm putting 1 minus cosine squared. You got to make that substitution to make it solvable. There's really nothing that you could do before that, except to try to think of the answers in your head, which of course would be very difficult. Now, I'm not saying that it's going to be easy to finish from here, but it's much more doable now. I could combine my like terms. I think this will factor, but if looking at this is intimidating to you, again, you can always just kind of sidebar over here and say, well, here's what it looks like as an algebra equation. And if I was asked to solve this, most people, although it's optional, would multiply everything by -1. So maybe I'll do that. And then this factors as an x minus 2 and an x plus 1. So then this means this guy would have to factor as a cosine x minus 2 and a cosine x plus 1. You can always check by foiling. It's the same thing though. Same logic behind it. So if I was having to solve this, I would set this equal to 0 and solve and get an answer of 2, and set this equal to 0 and solve and get an answer of -1. But over here, set this equal to 0 and solve, set this equal to 0 and solve. I get answers where cosine is 2 and where cosine is -1. Well, cosine's -1 right here. Cosine doesn't equal 2. There's nowhere where cosine is 2. So that half just didn't give me an answer. So it looks like pi, the only answer between 0 and 2 pi, and all the answers would be pi plus anything coterminal to it, plus however many rotations you want to do. If they land in the same spot, then they would have the same cosine value, which would still make that equation true. But the thing that's unique about this question is this sign's kind of problematic, but plugging in 1 minus cosine squared made it solvable at least. Get it to all one type of trig function. Okay, so we still need to look at double angle stuff, talk about some that are not possible, although we just kind of just saw that, and then a type of problem where algebra is not very helpful. Okay, so this one's a little unique because of this 2 here. So what I tell students to do is, for at least a moment, pretend like it's not a 2. Pretend like it's just a regular x. So it says cosine x equals negative square root of 3 over 2. So how would we go about solving that? Well, we've already done as much as we can here. We're already ready for the unit circle. I don't have to do a bunch of factoring and GCFs and all that kind of stuff. So I'm tempted to say this spot, which is 4 pi over 3, and this spot, which is 5 pi over 3. Okay, and then I could make a formula out of those that would give me all the answers plus 2 pi n. But the catch is, I pretended like this 2 wasn't there for a second. Now I need to go back and say, wait, I didn't solve for x, I solved for 2x. But that's not really a problem, because if I want to change this from 2x equals to just x equals, I want to divide both sides by 2. So divide everything by 2. And to change this from 2x equals to just x equals, divide everything by 2. And that would be your answers if the directions ask you to solve. Give every answer possible. Now in this type of question, we have to do these 2 backwards. I've been finding these answers and then going on to do these. This is like the formulas that tell us all the answers. So now let's use this. Here's where 2 pi over 3 is. It's saying 2 pi over 3 is an answer. So 2 pi over 3. But it says if I add pi to it, that should also be an answer. So if I added pi, that would be right here. And that's still between 0 and 2 pi. So 5 pi over 3 should be an answer. And then the second formula says 5 pi over 6 should be an answer. So go ahead and list it. And it says adding pi or subtracting pi should also give us an answer. Subtracting pi wouldn't be between 0 and 2 pi, but adding pi is still between 0 and 2 pi, so 11 pi over 6 is also an answer. So in that sense, you want to use the formulas here and backtrack and figure out which ones would fall between 0 and 2 pi. But really not that much different. You just have to be careful that you're not solving for x, you're solving for 2x, so you need to divide both sides by 2. So everything gets divided by 2. Okay, and I think this one was deserving of a second example. And the next one's a little messier, but same idea. So if I was trying to solve this, I would do as much basic algebra as I could first, like divide both sides by 2. And then I'd say, okay, this is one of those multiple angles, because there's a 3 right there. But I'm still going to start it off the same way. I'm going to ask myself, where's cosine x negative square root of 3 over 2? And so I'm tempted to say when x is 5 pi over 6 plus everything coterminal, and when x is 7 pi over 6 plus everything coterminal. The big asterisk, though, is I didn't really solve for x. I just did that for convenience. I really solved for 3x. I ignored the 3 for a moment, but now I have to deal with it. So divide everything by 3 to actually solve it for x. And divide this one, everything by 3. Now this one, the reason why I said it's a little messier is finding the solutions here is kind of a pain, and it's pretty tough to do without a calculator, to be honest. But we could quickly get two answers. We've got these two sitting here. We can see that these numbers are between 0 and 2 pi based on the fraction. The numerator is not twice as much as the denominator. So 5 pi over 18 is definitely 1, and 7 pi over 18 is definitely 1. But if I add 2 pi thirds to this one and it's still between 0 and 2 pi, then it's supposed to be included too. So without a calculator, you'd have to go over here and say, what do I get with these? I'd have to get a common denominator, and I'd need to think about if it's between 0 and 2 pi. I did that last class, and it's fine. It's doable. It's just a little taxing. So I'm going to have my calculator add those fractions together for me. Math, enter, enter to change it back to a fraction. And 17 pi over 18 is definitely between 0 and 2 pi. So I have to include it. Okay, and then try again. 17 pi over 18 might be 1, but if I add another 2 pi thirds, if it's between 0 and 2 pi, I need to keep it. So again, I've got it set up in my calculator to go pretty quickly here. That gives me 29 pi 18ths. And that's still between 0 and 2 pi too, because the numerator is not twice what the denominator is. So we would have to include it. Okay, if I added it again, I'm up to 41 pi 18ths, which is more than 2 pi, so I'm done with that part of the formula. Okay, then I could use this one, 7 pi 18ths plus 2 pi thirds. Again, getting a common denominator together and adding those is not that bad, but just for our time purposes here. That would give me 19 pi 18ths, which is between 0 and 2 pi, so include it. Take 19 pi 18ths, add 2 pi thirds, see if it's in the range you want. That gives 31 pi 18ths, which is still between 0 and 2 pi, so we'd have to include it too. And then if we added another one, it would be too much. So that 3, multiplying whatever we plug in for x by 3 means there's lots of answers just in one rotation. If it was something like a half, you get less answers. Something like 2 or 3, you end up with more answers. But I'm not so concerned about this part because, again, adding and subtracting fractions, given enough time, you can do that. But you really need to understand how I'm using this formula. This formula, 7 pi over 18 is one of them, and then I added 2 pi thirds to get another one, and then I added 2 pi thirds to it to get another one. You need to see where these are coming from. And then this one, 5 pi 18ths is right there. I added 2 pi thirds to it, got an answer, added 2 pi thirds to it, got another answer. All of those were between 0 and 2 pi, so technically they would work as solutions. You need to understand where I'm getting these from out of those. Okay, but that is the messiest by far. So this already kind of came up, but not all the stuff's going to be possible. So if you started this by dividing both sides by 5, and then you ask yourself, where's sine 5? Well, sine's never 5, so not possible. So you just need to understand that it is possible to get no solution here, or for a problem not to be possible. Or if you subtracted 8 from both sides, ask yourself, when is cosine negative 4? Well, cosine's not negative 4. Not possible. So you should see that a few times, and those are nice questions too. Like, obviously you have to catch that that doesn't make sense, but it's a lot less work than other ones. All right, and then our last example for our notes. Sometimes I don't think algebra is the best approach. So algebraically, you can, if you want to, you can square both sides of an equation. As long as you keep it balanced, it's fine. And you can go from here, and about 8 steps later, 10 steps later, you're going to get a couple answers. Some of the answers may not work though, because they're going to be extraneous. Anytime you square both sides of an equation, you might create fake answers. So if you got a bunch of answers, 2 or 3 answers here, the only way to know which ones actually worked would be to plug them in and see which one worked here. And some people prefer to do that, and that's fine. I'm not going to tell you not to do that, but what I think makes a lot more sense with this is it's stripped out. It's just saying if you took the sine value and took 1 away from it, it gives you the cosine value. Well, in the unit circle, all this stuff in the quadrants, these aren't spaced out by 1. This is what this is saying. They're spaced out by 1. Only right here are they spaced out by 1, and here, only the quadrantal angles are spaced out by 1. So I would just test those 4. Sine's the y value, cosine's the x value. If I subtract 1 from the y value, does it give me the x value? If I subtract 1 from the y value, does it give me the x value? If I subtract 1 from the y value, does it give me the x value? Subtract 1 from x, or y, it gives me x. Subtract 1 from y, does it give me x? To me, that's a whole lot easier, just thinking about which ones make sense. And again, I only had to test those 4 because those are the only 4 places that are spaced out by 1. And then, of course, I could get all the coterminal angles if the direction said pi, or solve instead. So I would recommend to you to take that approach when you see a question that looks like that, instead of the algebra approach. Algebra approach just is longer, and it still depends on you checking your answers by plugging them in at the end. I'm afraid that you'll forget to do that. Okay, so if you would kind of scan over your page, see if there's any immediate questions that you know you want to ask.